This is the GCSE Physics video series, video 3, for the topic of energy resources, covering lessons 15 to lesson 19. So, lesson 15. Here we're going to look at energy demands. And we're going to start by talking about this graph on the top right in the middle here. See, back in the 1920s, all of our demand, Britain's demand for electricity generation, was met by burning coal. Pretty much all of it. Maybe a teeny bit of wind, hydro, solar right at the top here, but no, it was burning coal. We did start using a bit more wind and hydro. It wouldn't have been solar, but using a bit of wind and hydro going into the 1930s, 1940s, 1950s. And as the 1960s started, we saw nuclear power take over in a big way in Britain. 80s, 1990s, 1995, around 1990 to 1995, we found gas in the North Sea, or under the North Sea. So we started mining for that, with oil rigs and stuff. And then our gas usage increased, which decreased the use, our dependence on coal. We also started importing stuff around 2010, and also around 2010 we started burning biomass, which is another carbon-neutral renewable resource. And so the use of coal diminished to almost nothing. I believe it did increase a little bit in the last few years, but I don't know what it looks like on this particular graph. This only goes up to just before 2020. So you can see that as soon as we could use gas, we started using gas, and there are various advantages to that. And this is all scaled to 100% of our energy usage. So our energy usage has increased continuously from 1920. Our use of electricity has continued to increase. But this just shows it scaled so that how much of what we used was generated by these different resources. So it's not necessarily that we're using less nuclear. In total, it's just the share of nuclear is decreasing because our usage is increasing. Perhaps. We don't have enough data. But it's an interesting graph. So why would we have switched from using coal to using gas? Well, there's a few reasons. One, it turns out it's cheaper. And two, gas is more energy dense than coal is. Three, gas is less environmentally damaging than coal is. But it's still not great because it's still a fossil fuel. Now, globally, most of the energy demands, generating electricity demands, are met by burning coal, oil, gas, fossil fuels. So over here on the right-hand side, you can see the global energy consumption. And this is only for the last 20 years. Well, from 2000 to 2020. It doesn't include anything that happened after 2020. And what can we see? Well, we can see that this tape is not... Is it scaled? I don't think this is scaled in the same way. And what do we see? Coal usage increasing, oil increasing, natural gas increasing. As our demand increased, so our supply increased of burning those three resources. Not ideal. We'd rather not be burning them. Now, you can see that over the last 5 years, there's a trend downwards for coal. I wouldn't say there's a trend downwards for oil, although this rather optimistic graphic from Wikipedia says negative 0.5% trend. The last 5 years, it was going up, and then there was a sudden drop. And that drop corresponds to 2020. And things happened in 2020 that rather affected our use of things like petroleum, petrol, diesel. We all stopped driving around because of the pandemic. So this isn't electricity, this is just energy consumption. So I think that's included in these data, is the use of things like petrol and diesel internal combustion engines, cars, lorries and such. And they usage dropped in 2020 due to globally there being lockdowns. So this drop here, I think it's optimistic to say it's a negative 0.5% trend. That does not look like a trend to me, but anyway. Natural gas usage, again, yes, it dropped a tiny bit in 2020, but, well, we weren't going out to restaurants and things, and I don't know if that has an effect. It probably does. Nuclear usage, pretty stable. Hydro, gradually increasing, but the encouraging graphic is this one. Other renewables. So that would be wind, and that would be solar power. And this trend, I mean, it might be an exponential increase. I don't know, I'd have to check, but it is very encouraging indeed. Because we need that to improve even further. Last chart, this one down here, pie charts, the worst type of chart there are. No one likes pie charts. Our primitive human brains are very good at looking at two bars of different lengths and working out which one is longer. It's not so good at looking at two sections of different angular sizes and trying to work out which one is bigger. It's not very good at that. You look at the blue and the green section, and the blue, yeah, you can kind of tell it's a little bit bigger than the green, but by how much, it's not easy to tell. And the orange and the black section, which one's bigger there? Well, it's the black one, but it isn't easy to tell. So, anyway, I'll stop moaning about pie charts. Here's a pie chart showing the world. Total primary energy consumption by fuel in 2020. So, yes, we can say it's encouraging that renewables is increasing, but overall, what have we got? We've got burning oil, burning coal, burning natural gas. Not great. Right, so how do our power stations work to generate electricity? We're going to cover that now. This picture in the middle shows a pressurized water reactor. So this is a nuclear power station. But actually, the fact it's a nuclear power station isn't that important. If you replace this yellow and red part in the middle here, if we replace that with, let's say, a furnace burning gas or a furnace burning coal, okay, we'd need something to powder the coal so it burns better. So we'd have to add something onto that. Or a furnace burning oil. I don't know if they exist. I must do. So, excuse me. So if we had a furnace here burning that, it's going to cause an increase in temperature within the furnace. So it's the same idea, though. We pump cold water through the furnace as a heat exchanger. The water boils, turns to steam. That steam, because of the way physics works, when you turn water into steam, the steam expands. It's a force outwards. It pushes outwards. It increases in area, in volume as much as it can. So that rushes through these pipes. That steam pushes around these turbines. And then we need some sort of system where we pump cold water into another heat exchanger so that that steam cools down and condenses back into water. We call that a condenser. The turbine itself is attached to a generator. So the turbine is just, like a wind turbine. They're just blades that when the steam hits them, it pushes them around. So along that axle, that's connected to a generator, which uses electromagnetic induction to generate an electric current. And then we've got various transformers and whatever else on the national grid, which isn't shown in this particular graphic. So this is a nuclear power station, so the only difference is where we get the heat from. Rather than burning fossil fuels, we take nuclear fuel, mainly uranium, maybe a little bit of plutonium, but mainly uranium, in fuel rods. They will get hot all by themselves due to a reaction that we'll talk about, nuclear fission, which we'll talk about in video 7. Don't worry about that now. So that will get hot. We just pump water through the core, which is getting hot due to these nuclear reactions. We pump water through that core, cooling the core down, but increasing the temperature of the water. So then that water we use in a heat exchanger, just as we did before. This water we have to keep this isolated because it's flowed through nuclear fuel and nuclear waste, so it is contaminated So we have to keep that in a special containment structure so it doesn't cause a risk to anyone outside. So that's the basic principle of what's called a thermal power station. A thermal power station is generating electric power, and it's called a thermal power station because the principle of operation is make water hot. Water boils, turns to steam. So we could burn biofuels as well, and biofuels are renewable. Biofuels, for example, we can make ethanol by growing certain crops. I don't know what they are, and then using yeast and sugar. So sugar, I guess, sugar beet or something, and using yeast to produce alcohol. And then once we've got the alcohol, we can burn the alcohol in the same way. They exist. They're not very popular. As you can see, biomass is a very small section down here. If you're growing crops to burn to make electricity, then you're not growing crops to eat. And in the UK, we're limited in space. So when there's global famine and all sorts, there are pros and there are cons to this. Biofuels, though, because you're growing stuff, that means you're removing carbon from the atmosphere. Then when you burn it, the carbon goes back into the atmosphere. So it's carbon neutral. We're not actually increasing the amount of carbon in the atmosphere by burning these biofuels. But we'd have to make sure we're not releasing soot into the air, because particles like that can affect the global climate and local climate as well. Last thing down here on the bottom left is looking at energy density. So fossil fuels, quite vague, but in general, fossil fuels, you're getting around 30 million joules of energy for every kilogram of fuel that you burn. And the downside is it releases CO2. But that's 30 million joules per kilogram of fuel. That's what we call the energy density. The energy density of uranium is orders of magnitude higher. 1, 2, 3, 4. 4 orders of magnitude higher. 300,000 million joules per kilogram. So that's 300 billion joules per kilogram that we're getting out of uranium. Of course, we're not burning uranium, but still. The energy density of that fuel is far, far higher. So you can see why it's quite an attractive energy resource to use. And it's carbon neutral, because we're not burning anything to release carbon dioxide into the atmosphere. So there are lots of pros to uranium. There are some downsides, but we'll talk about that later in this video, and we'll talk about that in the video 7 as well. Right, that's lesson 15. Lesson 16. We are looking and focusing in on different resources in particular. We're looking at wind, we're looking at water. Why the exam board decided to group these together, or in a textbook that we tend to use, I don't know, but there we go. So you need to learn these: wave power, wind turbines, hydroelectric power, tidal power. You need to learn how they work. Over here, we've got an example of wave power. It's not very good, but this buoy, which floats, or if you're American, buoy, it's a buoy, which floats, it rocks backwards and forwards because of the waves, and there's a mass which was going to swing backwards and forwards because of that motion. And you want to arrange it so the length of this arm is such that the mass will resonate with the typical wave frequency that is causing the whole structure to rock. Anyway, that arm is connected to a generator at the top. So as the arm swings backwards and forwards, it turns a generator, and by electromagnetic induction, just as we talked about before, that's going to generate an electric current. There are problems with this. It's sat in salt water, which means the parts are going to corrode more easily. It's not going to last very long. You can't use it when it's very, very stormy, because it could get damaged. And you can't use it when it's not very much wind, because then the waves are going to be very still. You're not going to generate anything from it. And you've got to have a big body of water like the sea for that to work. Wind turbines, here they are. These are very, very popular. You get wind farms that have lots of these wind turbines. Can't use them when the wind is too high. Can't use them when the wind is not high enough. Wind speed I'm talking about. When the wind speed is too high, when the wind speed is too low, you can't use them. But otherwise, wind hits these turn around, these blades turn around, and there's a generator at the top. Brilliant, works great. There are effects on wildlife. These do have an effect on things like birds. Apparently, they can make noise as the blades sweep around, which some people can find disturbing. Some people don't like how they look on the horizon if they're out to sea or if they're on a hillside. People don't like how they look. They refer to that as visual pollution or noise pollution for the sound that they make. But they're better than burning fossil fuels, certainly. What we've got down here at the bottom is an example of hydroelectric power. So water is held up high in a reservoir. Then we allow that water, using various sluice gates to control how much water we allow that water to flow into or through a turbine which is connected to a generator. Excuse me. So this water in the reservoir needs to be filled up. Mother Nature helps us with that by making it rain or having ice melting in the hillsides, and that water will flow down smaller rivers to fill up the reservoir. The environmental impact of this is that you're having to hold water back, which means there's an area in a valley which we are flooding with water, which would otherwise not have been flooded with water. That could be habitats for animals, will be habitats for animals, and the animals can't live there anymore if we flooded it. It flooded their homes. So that is the impact of this. Not perfect, but again, this is once you built the thing, it runs for decades and it's fairly cheap to maintain. So this is good for us, not so good for the animals that lived in the valley. So each of these, what's the energy transfer happening? Well, in the case of the first one, we've got the kinetic energy store in the water waves. Can we call that, or should we say that the waves are transferring energy to the kinetic energy store of the buoy? And then we are generating a current to transfer that energy somewhere else into the national grid. This one here, with the wind turbines, we've got energy in the kinetic energy store of the air, which is reducing, increasing the kinetic energy store of the blades, which is used to generate a current to transfer energy out of the kinetic energy store of the blades into, the national grid, to the other end of the national grid. In the example down here, we've got energy stored in the gravitational potential energy store of the water that's in the reservoir, and that's going to be transferred into the kinetic energy store of the water as it flows down. It's effectively falling water, and then we transfer that into the kinetic energy store of the turbine, and then we use the generator turning to generate a current to transfer the energy into the other end of the national grid. So that's those three. Tidal power is the same sort of thing as our hydroelectric power. Small difference though. With tidal power, you have the water. There's different ways of doing it. One is as the water flows in, it turns the generator one way. As it flows out, it turns the generator, probably designed to make it turn the same way, but it turns the generator whenever the water is flowing. So when the tide is turning, then the water is not flowing, so the generator stops turning. Another way is to use a clever system of gates so that when the tide is coming in, you fill up a sort of a basin, like a reservoir, but smaller. And then when the tide goes out, you slowly release that water through the turbine. So it's basically the same as hydroelectricity, except the water is replenished in the reservoir using the tides. How do you get the water up because of tides? Well, you're increasing the gravitational potential energy store of the water due to the moon. This is a misconception, okay? So wind is not caused by the moon. Wind is caused by differences in temperature of the air over the land compared to the air over the sea, and waves are caused by the wind. So waves aren't caused by the moon either. Moon will cause tides, but the moon doesn't cause waves, and the moon doesn't cause wind. Not really. Right, so the national grid, we're now going to define what the national grid is. we're going to talk about transformers and cables, but not the pylons. Even though they're owned by the company National Grid, they are not part of the national grid because the current doesn't flow through the pylons. We have current going into a transformer, current coming out of a transformer, current going along the electrical cables, but the pylons themselves are just holding the wires up in the air. So they're not part of the national grid, even though they're owned by the company called National Grid. So just be careful of that. Your thermal power stations are often, maybe even always, owned by private companies. So, for example, Sizewell B is owned by EDF. That's a private company. And the wires come out of Sizewell B into the national grid, which is a separate company. And that energy then, the current then, is carried by the national grid to your homes. And your homes are owned by neither the national grid nor EDF. So you've got to buy the energy. Okay, so here's a nice question at the bottom that I have seen come up, or a question similar to this has come up in an exam. It says, what happens to the wind power when the wind speed doubles? Wind power, remember we're talking about wind turbines, when the wind speed doubles. And your instinct might be to say, well, if the wind speed doubles, then the power will double. But what are you basing that on? You've got to think through the mathematics. So we are transferring energy from the kinetic energy store of the air. Kinetic energy store means we're using the equation E equals half mv squared. Okay, so if we are doubling the wind speed, then we have twice as much air passing through the blades per second. So that means that per second there's twice as much mass of air being delivered. So that would double the kinetic energy, except that the air is moving faster, so it's carrying more kinetic energy as well because of the speed of the air, not just how much air. So every kilogram of air that moves through the blades, if it's travelling twice as fast, it actually carries 4 times as much energy because the speed is squared in the equation. So every kilogram of air that flows through these blades carries 4 times as much energy, and we have twice as much air passing through these blades per second. So that means that we have twice as much air per second multiplied by 4 times as much energy per kilogram, therefore 8 times the power. It says here E equals half mv squared is increased by a factor of 8 at the bottom. That should say P. Imagine that we divide both sides of the equation by T. E divided by T is power. Covered that before. And mass divided by time, the rate of flow of mass is doubling if the speed is double. So it should be m divided by t on the right-hand side. And everything else in the equation works. Last thing I haven't mentioned is this definition of renewable. I don't like the definition, but this is the one that exam boards often like you to learn. Replenished by natural means at the same rate or greater rate than it is used up. Yeah, I prefer to say that it will not run out during the course of human civilization. I think that's a nicer way of putting it, personally, but hey-ho. So that was lesson 16. Lesson 17. Here we're going to look at the power from the sun and the earth. Again, weird to group these together, but there we go. We've got solar panels. Solar panels. We need to be careful here because solar power comes in 2 different flavours. We've got solar panels which involve water being heated up. So solar heating panels use energy transferred from the sun by electromagnetic waves. That's the mechanism, transfer of waves, to heat water. And we can use that. We can even boil water to generate steam, to turn a turbine, to turn a generator to generate current. We can do that. Something like this is a solar power station, basically a solar thermal power station. These are just mirrors on the bottom here. That's all they are, is mirrors. They look blue because they're reflecting the sky. And you can see the shafts of light being reflected off them, being scattered off the air. And the top part here is being water is being pumped up, cold water is being pumped up, heated up, and then that steam is gushing through through a generator. So that is what we could use with solar heating. The alternative to solar heating is using photovoltaics, a photovoltaic cell like this. Complicated how it works, so we don't need to go into the semiconductor detail about this, but effectively you've got light falling on these panels and a current being generated. There's no energy store inside here, really. I mean, there is. You could talk about electrostatic potential energy and all this sort of thing, but that's not listed on the list of the 5 energy stores, so we wouldn't need to bother. If I was going to do an energy transfer diagram for this, I'd just have light waves coming in with an arrow. I wouldn't have a store. I'd then have another arrow immediately after it saying current. That's what I would say. So this is what they look like. This is a solar farm that uses photovoltaics. Some people on the roofs of their houses have photovoltaic cells. Some people have panels that heat water, like I have. They're both examples of solar power, but they are very, very different. So be careful, because what do we mean by a solar panel? And it does change. Do check, but the most recent exams, when the examiner talked about solar panels, they were talking about the solar heating of water. And if the examiner wanted to talk about generating current from photovoltaic panels, photovoltaic cells, that's what they called them. Just be very, very cautious about just saying solar panels without thinking what it is. And I've even seen questions where they flip-flop between the two, and you lose marks if you're not being very clear about which one you're talking about. So that's your photovoltaic stuff here. There's some information down here you can read about the disadvantage. It needs a lot of space, needs a lot of mirrors for the solar heating, to use that as a thermal power station. These solar panels, by which I mean photovoltaic solar panels, are not very efficient. They waste about 90% of the incident energy just by reflecting it back off them. They're not very good in terms of efficiency. So it takes a lot of space to generate anything worthwhile, which we don't really have in the UK. They're good if you're remote and you don't need a lot of power for like charging devices, but other than that, they cost a lot to build. They use some rather unpleasant chemicals. Easy to maintain though, you just give them a clean, and they cost nothing to run, so that's all good. Some places in the world, the Earth's crust is thin enough that you can use geothermal energy. So geothermal energy, the rocks under the ground are hotter, so we just pump cold water down, hot water comes back up. Simple as that. There are some downsides to this. It can possibly increase the number of earthquakes that you get, because you've got water expanding into steam, and that can have an effect, possibly. Still being debated, that one. Advantages, we can just use that hot water to heat our buildings. We don't need to have to generate electricity from it at all. But systems like this, where you use the hot water, the steam in the hot water in a power station as normal, as a thermal power station, or water that comes out is still hot enough that we can use it in our homes. So this is a use of geothermal. You could do that in places like Iceland, where the Earth's crust is thin enough. Can't really do this in the UK. There isn't anywhere where we could pump water. We'd have to pump the water far too far down, so it's just no point. Okay. Next lesson. Which lesson is this? This is lesson number 18. Yes, energy in the environment. I made the graph here sideways on to make it fit, which was not ideal, but you can tilt your head or tilt your device maybe to watch what's going on with this. But this is the amount of energy, terawatt hours, shouldn't be a hyphen there really, terawatt hours, that's a unit of energy, a huge unit of energy that's been generated, and along the x-axis, which is drawn vertically, we've got time, and you can see that the amount of energy this can't be in total, so this must be per year. It's not clear, but the amount of energy that we are generating with fossil fuels per year is actually dropped, which is good, and renewables has been increasing, and there's that almost exponential increase which we were hoping for. Hydro's not really got off the ground because it's so limited where you can build it. Nuclear had its heyday in the late 1990s, but it's still chugging along there. We need to get the fossil fuels down to zero. That's a desperate thing. So facts at the top: coal, more greenhouse gas than oil; oil, more greenhouse gas than gas. So we're happy to use gas rather than coal or oil, but we'd rather use something other than gas if we can get away with it. There are other things we can do with gas. So the fact that gas is flowing through our pipes, you can do what's called a combined cycle gas turbine, where you don't just burn the gas to use it in a thermal power station. The gas itself flowing, you can connect a turbine to that as well. So there's all sorts of clever things. You can the exhaust from the combustion of the gas, you can use that to generate electricity as well. So here are some fuels. I've only listed 3. Fossil fuels, I've bunged them all together, but do name which ones in an exam. Nuclear fuels, so uranium, plutonium, mainly uranium. Don't know why they include plutonium. It's an irritating byproduct of uranium. And renewables, I've bunged them all together there. So you've got some advantages. You can read these yourself. I'm not going to read them to you. You can pause the video and read them yourself. Greenhouse gases, disadvantage. There's 2 main ones that we can talk about. Sorry, 2 main disadvantages to burning fossil fuels that we could talk about. One is greenhouse gases being released. One is sulfur dioxide being released, which can cause acid rain. They're also non-renewable. So is nuclear. Nuclear is non-renewable as well. Be careful of this because I have seen students absolutely convinced that other teachers in other subjects have told them that nuclear power is renewable. It's not renewable. It is what we call recyclable, in that the first time the fuel is used in the reactor core, all of the fuel isn't used. We take the uranium fuel rod out of the reactor core when it's stopped being useful, but then we can process that by removing what little uranium has actually fissioned, and then what we've got left we could put back in the core. So that's recycling the fuel, but that's not renewable. That process can't go on forever and ever. So it's definitely not renewable. Then we've got disadvantages of wind, disadvantage of tidal, hydroelectric, solar. So you can't just say, oh, renewable resources are unreliable, because that's not true. Tides are very reliable. Hydroelectricity, fairly reliable. Whereas solar, well, day to day, is not so reliable because of cloud coverage. Wind, not very reliable because wind speeds change day to day. So don't just say, oh, renewables aren't reliable. You've got to be a bit more specific than that. Some renewable resources are unreliable, but some of them are fine in terms of reliability. Droughts affect hydroelectricity. Yeah, that's true. We can usually manage that, though. It's only a couple of times in the year, maybe even once a year, when we start getting a bit worried about our reservoirs getting a bit low and hose pipes get banned and people are told not to wash their cars and stuff. Anyway, you can read that yourself. So let's move on to lesson 19. Lesson 19 is the last lesson for this video. Big energy issues. And as is the case in most engineering situations, the biggest issue is money. So if we have a look at these resources, these are all scaled compared to gas. So capital cost, gas is 1 times the cost of gas to set up. That's what I mean by capital cost, build the stuff. And the overall cost, that's running and decommissioning and everything else, gas is as expensive as gas, 1 times the cost of gas overall. Well, of course gas is. So that's what these numbers mean. We just scaled it relative to gas. Coal is a little bit more expensive than gas overall, a lot more expensive than gas, 5.5 times as expensive as gas to build a coal power station. Now, why is that? Well, you've not just got the coal power station, you've also got to have all the infrastructure that moves a solid like coal. Gas, you can pump it through pipes, but coal, you've got to have the train stations, not train stations, train lines in order to transport all the carriages full of coal. Plus, you've got to have a mechanism to grind the coal up and turn it into a fine powder, which is what I think they tend to use. So that's actually more expensive to build a coal power station than it is to build a uranium power station, a nuclear power station. Nuclear power stations 5 times as expensive as gas power stations to build. Hydroelectric 3 times, wind 6. You can read this yourself. The overall cost, which is an interesting one, hydroelectric works out to be cheaper overall. Mostly because they last with very little maintenance for a very long time. So hydroelectric over the decades that the power station is running, well, we don't even have to decommission them really. So that's it. That's 0.7 times cheaper than gas, but we are so limited where we can build these things. So that's why we don't just use hydroelectric power. What else we got? Nuclear power stations, uranium, only a bit more, only 10% more expensive overall than gas. And given the huge advantages, stammering over my words there, given the huge advantages of nuclear power in terms of the environmental impact of global warming being less if we're using uranium instead of gas, I think the 10% increase in everyone's bills is probably worth it. What else have we got? Wind, well, 2.2 times, so 220% increase in everyone's bills. Well, it wouldn't be 220%, it'd be 120% increase in everyone's electricity bills. I think people are going to get upset about that. But that's what we're talking about with wind. Solar, so 90% increase, nearly doubling our electricity bills. It's going to be a lot of resistance to that as well. So this is a table that's worth considering, worth keeping in mind in terms of costs. That's one consideration. Another consideration is how you would meet the demand with these power stations. So over the course of a day, and I just picked a typical day, I picked the 2nd of January 2020. I picked the 2nd of January just because I wanted a day in the winter when it was pretty cold. I didn't want to pick New Year's Day because I thought that's not going to be a fair representation. The 2nd of January, some people are back in work, so I thought this was a good day to pick. And the black line on this graph shows from midnight all the way through the 2nd of January to midnight. So all of this graph shows the 2nd of January on that day. This is what the demand in Great Britain was doing. And you can see the demand was lowest around 4 a.m. when all the teenage gamers finally went to bed. And then in demand increases steadily up to around lunchtime. Then it stays pretty constant, drops a tiny bit, but this is during the working day. And then it peaks at around 5 o'clock, which is when people are generally cooking their evening meals, relaxing, and then people start going off to bed, and the demand drops down again, but stays level for an hour while, between midnight and 1, while all the teenage gamers are playing on their games consoles. So that's what the demand looks like over a typical day. Now, if you try and do some sort of averaging of this. Now, what I've done, this red line cuts this picture so that the red area underneath is equal to the green area above, well, approximately, as well as I could do it. So the green area above is equal to the red area underneath. Imagine we were generating power at the level indicated by this red line. So that's 31,000 million watts. Now, during night time, we're wasting power. What can we do with it? All we're doing is heating up the wires in the national grid. We can't actually do anything with it. But imagine that we were able to store every bit of energy that we were making during the night time that we weren't using. Making's the wrong word. Generating. Yeah, let's just call it that. Imagine we were able to store it all somehow. Then, when our demand exceeds 31,000 million watts, we would have that store that we could make use of to fill this gap. Now, if we did this and there were nothing wasted in this process, then we would be consistently generating the same power all the time, and we would be happy with that. We'd be wasting nothing ever. The problem is that we can't store the energy in the way that I'm describing. You might think we use batteries, but the size of these batteries would be astronomical. Batteries also don't last forever, and they use some pretty unpleasant chemicals in them. So what do? We use what's called pumped storage. During the night time, we pump water up into a reservoir, so we're using this energy that's being generated to drive the pumps to pump water up into the reservoir. Then, during the daytime, we've now got more energy stored there. We just open the sluice gates a bit more on our hydroelectric plants, and the water flows down a bit faster to try to meet that demand. So that's what we do. But we cannot get anywhere near the 100% efficiency that this graph would want to show. So how do we track this changing demand? Well, what we need is power stations where we can very quickly change the power output. Now, gas is the best for this. It has a very short startup time. So with gas power stations, it doesn't take very long to change the output. You can very, very quickly change the output to track what the demand is doing. Oil's a bit slower than that. Nuclear is even slower. Coal is even slower. Nuclear, it can take days, maybe even weeks, to change the output from a nuclear power station. You cannot track what the demand is doing with our power station, with the nuclear power. You can't just turn it up, turn it down again. They did that once in the sort of mid-1980s. They messed around with the power station a bit too much, changing the power output too quickly, and it caused a bit of a problem. A little bit of a problem. Look it up if you're not aware of it. It's called Chernobyl. So yeah, nuclear power, you've got to work slowly with that. Startup times and shutdown times for nuclear power is very slow, whereas gas, much faster. Right, okay, so let's now look at the left-hand side of this. Our hydroelectric's unreliable because of droughts. I mean, this is stuff we've already talked about. It's just put up here again for you. Nuclear and fossil fuels provide a base load demand, a base demand level. So this red line, this imaginary red line, is what we would call a base load demand. It's not changing over time. We can increase the output from gas, yes, but gas isn't the only one we use. Nuclear is pretty good for providing a baseline. But then we can use pumped to try to increase the output from our hydroelectric to try and follow the demand. That works quite well. As I say, gas is usually used as well. The problem with renewables is you can't say, I'd love the wind to be stronger during the day and slower during the night time. You can't make that happen. And actually, yeah, solar power is good because it's usually sunny during the day and dark at night. That's the usual way that the day and night cycle works on Earth. But there might be cloud cover. You can't rely on it and things like that. So we can use renewables to try to meet the demand when it exceeds the base load. But the base load, we want it to be high enough that we're not suddenly caught out and we have blackouts and power cuts where the national grid isn't able to deliver enough energy because the power stations just aren't providing enough. This bit down here just explains what I've just explained. So that was the video 3, all about energy resources. If you've liked that, just please do bear in mind I do live tuition, which is very different to these videos. It involves lots of backwards and forwards communication, me asking you questions and you answering them, you asking me questions and me answering them, that sort of thing. If you're interested in that, go to physicswithkeith.com and have a look at the enrolment process for those weekly sessions. You might find them useful. There'll be another video coming in soon, all about electricity, I think. So stay tuned. See you.